we would discuss a small sample tests. There is slight difference between large sample test and a small sample test. If we have understood well the large sample test, there would be no problem in understanding a small sample tests. If we have to test a single mean, that is, if our null hypothesis is mu equal to mu naught. Now, one thing you notice here, that this is our test formula. Now, here you see that this test formula is not denoted by Z. It is denoted by T. So this is the first difference, that for large sample, we denote it by Z, it is Z test, but for a small sample, that is when sample size is less than 30, it is denoted by T. Formula is the same, almost same. For large sample, you remember the formula was this one. I have given it here just for ready comparison between the two. You see what is the difference? The difference is that this we have denoted by T and this we have denoted by Z. The difference is that here we have n minus 1 and here we have n, and that's all. What is more important in this case is that is in a small sample test, that this time we would not compare with 1.96 and 1.64. When the sample size is small, when we are dealing with a small sample test, then the value of T would be compared with tabular value of T. There is a table which we call T table. So we would read the value of T from that T table at n minus 1 degree of freedom. A new term I am using, degree of freedom. So we should remember that in this case, that is in the test of single mean, the degree of freedom is n minus 1. Now let us take one example. A fertilizer mixing machine is said to give 4 kg of nitrate. We have taken a sample of 5 bags, and in those 5 bags we have these amount of nitrate available. We have to test whether the machine is functioning correctly or not. That is, whether the machine is filling 4 kg of nitrate in each bag or not. So here we would find the sample mean, that is mean of 2, 6, 4, 3, and 1. That comes to be 3.2. We would calculate the standard deviation, sample standard deviation of 2, 6, 4, 3, and 1. That comes to be 1.7. Our null hypothesis is mu equal to 4, because we have to test whether the machine is filling 4 kg of nitrate in each bag or not. And the formula is this. The value of T is coming to be 0.94. Now this 0.94, we would not compare with 1.96. We would take the value of T from T table at 4 degree of freedom. Why 4 degree of freedom? Because degree of freedom is 1 less than sample size, that is n minus 1. So this is T table. This is degree of freedom. 4 is here. We have to test at 5% level of significance. You see, it is 2.78. So the calculated value of T would be compared with this 2.78. If the calculated value of T is greater than 2.78, reject, because the difference is large. So this is the only difference between large sample and a small sample tests. Here we have to consult T table. And degree of freedom is important. We should always remember that degree of freedom is n minus 1, 1 less than sample size. Now, test of equality of two means. In a small sample tests, you see in large sample test, we had denoted it by Z. Now we are denoting it by T. X1 bar, X2 bar, all we know, these are the sample means. N1, N2 are sample sizes. S we would calculate by this formula, where S1 and S2 are the two sample standard deviations. So we would calculate this one, the value of this. And here, we should remember that in this case, the degree of freedom is N1 plus N2 minus 2. So you see, degree of freedom is important and we should remember it. In equality of two means, the degree of freedom is N1 plus N2 minus 2. Now, if our first sample is 8 and second sample is of size 7, then what would be the degree of freedom? 8 plus 7 minus 2, that is 13. So we would consult T table at 13 degree of freedom and 5% level of significance. If the value of this T is greater than that, we would reject the hypothesis. Now, here itself, we would test one very interesting and useful test, which is known as paired T test. Paired T test is also used for testing the equality of two means. But what is special about this paired T? We have already used the equality of two means. In paired T also, by paired T also we test equality of two means. The difference is this, that here the values are given in pairs. The two samples are not independent. Let me give one example. Suppose that there is a drug, antihypertensive drug, and it is claimed that this drug is very much effective in controlling hypertension, controlling high blood pressure. Now, for testing this one, you will conduct one experiment. You will take some patients suffering from hypertension. Suppose you have taken 20 patients. You will measure their blood pressure. You will treat those patients with that drug. And after a sufficient period of time, again, you will take the measurement on their blood pressure. Now, on each patient, we have two observations. One, before giving the drug. The second, after giving the drug. So here, if we have to test the equality of two means, we would apply paired T test. I will tell you one thing how to judge that this test is based on paired T. Paired T test is used in all those cases where the experiment is done or the observations are taken before treatment and after treatment. That's all. Before treatment, this is the measurement. After treatment, this is the measurement. So there we would take pair T. Pair T is denoted by this one. T, D bar. D is the difference between the two observations before treatment and after treatment. This S is the standard deviation of the difference. We would calculate the value of T, and again if this calculated value of t is greater than the tabular value of t at n minus 1 degree of freedom, then we would reject the hypothesis. So you see, the difference is only in the test statistics, in the test formulae. Afterwards, once you calculate the value of those test formulae, the procedure is the same. For large sample, 1.96, 1.64. For a small sample, tabular value of t at a given degree of freedom. Now, I am skipping this example because we have to discuss two very important and interesting tests which are known as test of independence of attributes and test of goodness of fit. These two tests are based on chi-square. So we call it chi-square tests. Now, what is test of independence of attributes? Let me put some questions to you. My first question is, does smoking cause cancer? Suppose I want to know. Does smoking cause cancer? What does it mean? I want to know whether there is any association between the smoking habit and the disease cancer, or are they independent? So this comes under test of independence of attributes. The third, can we say that the higher the level of education, the greater the degree of adjustment in married life? Here also we are talking about two attributes. One is the level of education and other is the degree of adjustment in married life. Is there any association between these two attributes? Or are these two independent? Does education level have impact on keeping a small family size? Is there any association between educational level and family size, or are they independent? So such type of questions we can answer by test of independence of attributes. Now, test of independence of attributes we generally do in a table, a special table, which is known as contingency table. Now we will ask, what is a contingency table? Very simple. A contingency table is made up of rows and columns. Now this is a contingency table. There are two rows. One row is of male, another row is of female. Total do not consider as row. There are two columns. So this table is made up of two rows and two columns. It is a contingency table. And generally we say that the size of this contingency table is 2 into 2. Number of rows by number of columns. As we express the size of room, 10 by 12. Like that, the size of this contingency table is 2 into 2. This is another contingency table. You see how many rows are here? 1, 2, 3, 4. How many columns? 1, 2, 3, 4. There are 4 rows and 4 columns. So the size of this contingency table is 4 into 4. So test of independence of attributes are generally done in contingency table. Now let us take one example. And before that, the formula that we would use for testing the independence of attribute is this one. This we call, pronounce as chi-square. So chi-square is summation. Summation you know, sum. OI minus EI square by EI. What is OI? Observed frequency. What is EI? Expected frequency. O for observed frequency, E for expected frequency. So observed frequencies would be given to us in the contingency table. Expected frequencies we would have to calculate. I will tell you how to calculate expected frequencies with the help of one example. Suppose that this is the example. Two sample polls of votes for two candidates A and B for a public office are taken from the residents of rural areas. The results are given in the table. Examine whether the nature of area is related to voting preference in this election. What is the question? The question is that there are two candidates, A and B. They have got votes from rural area and urban area. Our point of interest is to know whether the nature of area, that is rural or urban, has something to do with the voting pattern to the candidate A and to the candidate B. Is it so that the candidate A is getting more votes from rural areas and candidate B is getting more votes from urban areas? If it is so, then we would say that there is association between the nature of area and the two candidates. So here, our observations are given in this contingency table. There are two rows, rural, urban, two candidates, A and B. It is a 2 into 2 contingency table. These are observed frequencies, 620. That is, candidate A has got 620 votes from rural area. Candidate B has got 450 votes from urban area. So this is the meaning. So there are 4 observed frequencies, 620, 380, 550, 450. Now we have to find the expected frequencies. These are observed frequencies, OI. We have to find E. How to find expected frequency? You see how simple and interesting it is. Suppose that we have to find the expected frequency for this cell. You just take the row total, 1000, take the column total, 1170, multiply these two and divide by the grand total, 2000. So the expected frequency for this cell, where the observed frequency is 620, is 1170 into 1000 divided by 2000, that is 585. If you have to find the expected frequency for this cell, you just see the row total 1000, multiply it with the column total 830, divide by 2000. You will get the expected frequencies. So in all contingency tables, we get expected frequencies like this: row total into column total divided by grand total. So all the 4 expected frequencies are obtained and the value of chi-square is calculated. The value of chi-square comes to be 10.089. Now, in this case, we would compare it with the chi-square value. There is a table which is known as chi-square table. As T table, there is separate chi-square table. So in chi-square table, we would get the value of chi-square at given degree of freedom. What is degree of freedom here? Very interesting and very simple, you see. You can calculate degree of freedom in all the contingency table. Number of rows minus 1 multiplied by number of columns minus 1. Here number of rows is 2. So 2 rows is 2. So 2 minus 1, 1. Number of columns is 2. So 2 minus 1, 1. 1 into 1, that is 1. So here degree of freedom is 1. So we would consult the value of chi-square from the chi-square table at 1 degree of freedom. And if this calculated value is greater than that tabular value, we would reject the hypothesis. The rest procedure is the same in all the cases. If the value is greater, reject. So here, the tabular value is 3.841. Obviously, 10.089 is greater than 3.841. So the null hypothesis is rejected. Now, one point I missed to tell you, and that is very important point, that in test of independence of attributes, you may ask that what should be our null hypothesis. Please note it, that in test of independence of attributes, we always take our null hypothesis denoting the independence of the attributes. Whatever may be your language of the null hypothesis, but that must reflect the sense of independence of the two attributes. So here our null hypothesis is that area, the nature of area doesn't have any impact in the voting pattern to the two candidates A and B. And that is rejected. That is rejected means that no, nature of area has some association, has to do something with the voting pattern to the two candidates A and B. So in all contingency tables, we do it like this. Now, the next is test of goodness of fit. I will just take 2 minutes time because after that there is question and answer session. Test of goodness fit, this is another test which is based on chi-square, and this is also very interesting and important. Let me put some questions to you which will make us clear that what we mean by test of goodness of fit, what we mean by goodness of fit. Suppose our question is that do weekdays have influence on road accidents? Many people believe that on Saturdays there are more road accidents. Many people believe that in the weekend days there are more road accidents. Now we have to test whether days have any impact on the road accidents. It is test of goodness of fit. Do human beings have blood group O, A, B and AB in the ratio 1:2:2:1? Suppose that somehow it has come in my mind that the ratio of the persons having blood groups O, A, B and AB are in the ratio 1:2:1. If there is one person having blood group O, there are 2 persons having blood group A, 2 persons having blood group B, and 1 person having blood group E. So this is one pattern in my mind. I will find the observed values and I would test whether this hypothetical pattern which I carry in my mind, which I have believed somehow, does it fit with the observed pattern or not? This is goodness of fit. Now, in this goodness of fit also, the formula is the same, chi-square, same formula as we have used in the test of independence. The only difference is that here the degree of freedom is n-1. We should remember this one. Now let us take, let us take this example. These are the weekdays and these are the road accidents. The question is, are the accidents uniformly distributed over the weekdays? Now, the total number of road accidents over the 7 days is 84. If the road accidents are uniformly distributed over all the 7 days of a week, then what should we expect? We should expect in that case that 84 by 7, that is 12. So we would expect that on Sunday there should be 12 accidents, on Tuesday 12, on Wednesday 12, and in this way on Saturday 12 accidents. So the number of accidents is uniformly distributed. This is our pattern in our mind. Now we have to test whether this observed pattern, because we have observed that on Sunday there are 14 accidents, on Monday there are 16 accidents, on Tuesday there are 8 accidents, like this. Whether this observed pattern fits with this expected pattern or not. The same formula we would use. 14, 16, 8, 12, 11, 9, 14. These are the observed frequencies. 12, 12, 12. These are all the expected frequencies. Substitute in this formula. Calculate the value of chi-square. In this particular example, the value of chi-square comes to be 12.59. Now this 12.59, we would compare with the tabular value of chi-square at what degree of freedom? n-1. How many values we have taken? 7. So 7 minus 1, that is 6. Degree of freedom will be 6. So if the calculated value of chi-square is greater than the tabular value of chi-square at 6 degree of freedom, we would reject the hypothesis. So this is test of goodness of fit. The same chi-square formula we use here. It is the test whether our hypothetical pattern, the pattern which we believe fits well with the observed pattern or not.